So today's projects are for my zoopers. Um, Here's one of the pours from the other day, and it's a nice one. Another one. Here's one from yesterday. It's interesting because there's a separation of metals across the middle, and the top is the real shinier stuff. And it's kind of goldish colored. The bottom's really goldish colored. Very interesting. And here we see the separation of metals again. And that happens as the melt cools, different things crystallize out at different temperatures. And this is a spontaneous dendritic crystal of AuPT. PD. AuPD. It weighs almost nothing. Maybe less than nothing. I don't know. They're very light. They don't weigh hardly anything. And yet, they are precious metals, right? Just like gold and platinum. Prettier, even, maybe, because it's got gold and platinum in it. But not much. Not enough to make it heavy, anyway. And again, dendritic crystals. This dripped off the side of the crucible. Okay, and I have, there's one from yesterday. Needs zoopering. These guys, some guys have brass ones, I've got palladium ones. And onomas, look at this guy, isn't that beautiful? The tetrahedron with an innie on one side and the outie on the other. It's face-centered, cubic. And look at that crystallization. Isn't that just lovely? Wowie. So we'll clean that guy up today. Finish cleaning this one up. See if we can't ring a bell. Look at this. This is interesting. This is one of my stirring rods, carbon stirring rods. And it has a ring of palladium. I'm going to be careful here. It's got a little stuff on the end. There it comes. Look at that. So that got stirred around and around, and you can see it. Isn't that cool, huh? Wowie, man. I mean, that's like wowie. So we'll leave that one for a little later. And see what other kind of trouble we can get into. These are all kind of cool. Alright, so that's part of today's project. Just to get warmed up. Ooh, what's this? This is a former piece of solder, I think. It started out as a piece of solder. It's now a cobra striking. Look at that. Joof. Wowie, huh? So, this is palladium foil. It's dense enough to stop stray radiation in space. Things like the Van Allen belts, for instance, as you're on your way to the moon, you need to accommodate the radiation in the Van Allen belt. So all the charged particles from the sun come flying off of there at light speed and passing by the Earth. And if we didn't have an electromagnetic field created by the planet turning, all that radiation would be hitting the Earth, and there wouldn't be any life on Earth. Instead, the Earth is made of 3 different layers, inner core, and they told us it was nickel and iron early on, and I'm pretty darn sure that it is in fact AU and PT, aluminum or gold and platinum. And if you think about it, they're the heaviest things, and they end up in the middle, right? And they're magnetic. They are definitely magnetic, right? Because AU has one more proton-electron pair than PT does, and so they can't help it. And when you spin them around and around, that magnetic field also goes around and around, and it's the going around and around part that creates electricity in other things, right, in solid matter. And so the semi-molten mantle sits around that and allows the core to be separate from the crust of the Earth. And the crust of the Earth sits like this on the, this would be the continental shield, and I mean, it looks like this to us because we're little ants, right? It's actually kind of more like this. Flattish, and except where I live in the mountains. And that's because the crust of the continent cracked where a large anomaly hit in New Mexico about 100,000 years ago, I think. And anyway, but this is from the dust that kicked up It cracked the crust of the planet because it hit more than once. It hit, 4 or 5 times. And each time it fell from low Earth orbit, or at least the first time, I don't know what happened when it bounced, but it was moving at almost light speed when it hit. 17,000 kilometers an hour with per second acceleration turns into 277,000 meters per second when it hit the ground. It was fusing the atmosphere on the way through. And this stuff is the volcanic ash that came from at least 2 rounds, maybe 3, 4, I don't know, rounds of planet-wide volcanism. Volcanic activity that I'm not just talking about 1 or 2 volcanoes, I'm talking about all of them going off at once because when that ship hit, it hit so hard it cracked the crust of the planet. Australia has what they call the Great Basin. That's what it's from. And the tremendous heat of that pressure is what caused the opal fields around the Great Basin. That's I've been looking for the chemical formula, right? And the chemical formula is volcanic ash with real high palladium content, like the white stuff out of Lightning Ridge, and or out of South Australia, right? Cooper Pedy and those places, and the whiteness of that clay is just little tiny bits and pieces of palladium. You can see the rainbows in it, because the unit cell here, which is it's not just single atoms all joined together. There's like a group of atoms that make up the smallest crystal structure, the smallest cubes within the crystal lattice, and they form these little cubes. Gold on one side and platinum on the other, in a 3-dimensional checkerboard, right? So they're cubic, but they are half the size of a wavelength of visible light, and that means that when light hits one and it bounces from one side to the other of it, it's just traveled the distance of a wavelength of visible light. How about that? And it works like the little laser thingummies that credit card companies use and stuff. Those little line things that make rainbows. That's what this is. And we're dealing with the planes of cleavage in palladium. And it just happens that it's really, really white, and it's half the size of a wavelength of visible light. Like, whoa, fuck me. Whoops. Hey. Which makes it easier to identify. There are not many metals that make rainbows. But, from Starfire Family Industries, that's what we specialize in, is rainbows. Peace, y'all.